11.6 Absolute convergence and the ratio and roots tests. Given any series, the sum of a sub n, we can consider the corresponding series. The sum from n equals 1 to infinity of the absolute value of a sub n equals absolute value of a sub 1 plus the absolute value of a sub 2 plus the absolute value of a sub 3, whose terms are the absolute values of the terms of the original series. Sidebar, we have convergence tests for series with positive terms and for alternating series, but what if the signs of the terms switch back and forth irregularly? We will see in example 3 that the idea of absolute convergence sometimes helps in such cases. Definition 1. A series, the sum of a sub n, is called absolutely convergent if the series of absolute values of the sum of absolute value of a sub n is convergent. Again, the definition, a series, the sum of a sub n is called absolutely convergent if the series of absolute values, the sum of the absolute value of a sub n is convergent. Notice that if the sum of a sub n is the series with positive terms, then the absolute value of a sub n equals n, and so absolute convergence is the same as convergence in this case. Example 1, the series of the sum of n equals 1 to infinity of open negative 1 closed to the power n minus 1 over n squared equals 1 minus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus and so forth is absolutely convergent because the sum of n equals 1 to infinity, the absolute value of open negative 1 closed to the power n minus 1 over n squared equals the sum from n equals 1 to infinity of 1 over n squared equals 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus and so forth is a convergent P series P equals 2. Example 2. We know that the alternating harmonic series, the sum from n equals 1 to infinity of open negative 1 closed to the power n minus 1 over n equals 1 minus 1 half plus 1 third minus 1 quarter plus and so forth is convergent. See example 11.5.1, but it is not absolutely convergent because the corresponding series of absolute values is the sum of n equals 1 to infinity of the absolute value of open negative 1 closed to the power n minus 1 over n equals 1 plus 1 half plus 1 third plus 1 fourth plus and so forth, which is the harmonic series, open P series with P equals 1 and is therefore divergent. To definition. A series, the sum of a sub n is called conditionally convergent if it is convergent but not absolutely convergent. Example 2 shows that the alternating harmonic series is conditionally convergent. Thus, it is possible for a series to be convergent but not absolutely convergent. However, the next theorem shows that absolute convergence implies convergence. Number 3 theorem. If a series, the sum of a sub n is absolutely convergent, then it is convergent. Proof. Observe that the inequality where 0 is less than or equal to a sub n plus the absolute value of a sub n, which is less than or equal to 2 times the absolute value of a sub n, is true because the absolute value of a sub n is either a sub n or negative a sub n. If the sum of a sub n is absolutely convergent, then the sum of the absolute value of a sub n is convergent. So the sum of 2 times the absolute value of a sub n is convergent. Therefore, by the comparison test, the sum of open a sub n plus the absolute value of a sub n closed is convergent. Then the sum of a sub n equals the sum of open a sub n plus the absolute value of a sub n closed minus the sum of the absolute value of a sub n is the difference of two convergent series and is therefore convergent.